Hi guys. So I'm sorry I'm not there today in person. I'm really not feeling well. I'm going to try to make a short video introducing some of the ideas about triple integration, an example of a triple integral, how it's used, interpretations of triple integrals, and then we're going to move on to begin talking about change of variables. So the hardest part about visualizing what a double integral is that there's not really a natural way to think about a four-dimensional surface where you have three input variables and then a fourth variable somehow describing a surface above it. I mean, that's a thing that exists, it's real, but it's hard to visualize. So the analogy that I want you to have in mind when you look at a triple integral, this is what most people do, is in the same way that we can think of the double integral over an area of a function dA as essentially taking some region, let's call this D to be consistent here, some region D, cutting it up into little rectangles, and then in each rectangle, we're assigning to that rectangle a value, like a temperature or an energy density or something like that, right? And so that what you're doing when you add up the area multiplied by this sort of density is that you're recovering something like mass, right? So that, you know, if you have a distribution of something in a flat surface and you multiply it by the area of the surface, then you end up with the quantity of whatever it is that you're trying to measure. The same idea works here, where you know, the other interpretation of the double integrals is that there's a surface there and that you're looking at the volume underneath it, but that's hard to visualize with triple integrals. So instead, a sort of better way of thinking about it is you imagine that you have some region in space, so B, and it's three-dimensional. And then in that, you've chopped it up into little tiny pieces, little volume bits floating around inside of it. And you have a function f that tells you what the density is, so mass density if you want, or energy density, all through the surface. And so to this little box, you assign a quantity f of x, y, z that represents the density in that area, or the density in that region. And if you take density times volume, then you get whatever quantity is that you are after. So mass, if you were looking at mass density. But the idea is to think of f as assigning density, and then what you're doing with the integral is you're adding up the total of whatever it is that you have the density of. Okay, that's an easier way to think about it. So f is sort of distributing a density in space. So one of the quick observations that you can make is that if f was the function that assigned a density of 1 everywhere, then this integral will actually just recover the volume of the shape. So if f is just the 1 function, excuse me, then the triple integral over b of 1 dv, this is just the volume of b. So it's a useful fact sometimes. If we can describe b in terms of three curves, three sets of equations that describe the three-dimensional volume that we're looking at, I can just integrate an iterated integral and calculate the volume of the shape directly from that. So triple integrals also satisfy a Fubini's theorem type rule, where we can turn a triple integral into a triple iterated integral if we're working over a region of a particular type. And so just like in the two variable case, there are regions of different sorts of shapes, type 1, type 2, and type 3 elementary regions. It's less important to know how to classify those regions and more important to be able to read off from your picture, and these are much easier to do with pictures, to read off from your picture what the volume should be. So let's just describe a shape and see if we can integrate it. So as an example of how triple integrals get used, imagine that we have a solid W, so W is a solid, obtained, so you bound it with a hemisphere, x squared plus y squared plus z squared is equal to 4, where z is less than or equal to 0. And so the idea here is that we are describing the bottom half of a sphere, and then we're gonna attach to the top of it a paraboloid z is equal to 4 minus x squared minus y squared. If you want to visualize the region that we want to work with here, you can imagine that you have a hemisphere on the bottom that looks like this. This is x squared plus y squared plus z squared is equal to 4, where z is negative. And then to that, we glue a paraboloid that joins up right at this edge right here. So the paraboloid sits like this. And this is described by the curve z is equal to 4 minus x squared minus y squared. Okay. And the question might say, describe this region, right? So describe this region in terms of functions that I could use to find the volume of this if I wanted to. So the way that you do this is, at least the easiest way to do it is to think, okay, if I could turn this into a domain of functions x and y, where for any x and y that I chose, I could figure out what the volume is, or the height is to get from a top bounding curve to a bottom bounding curve, then I could actually describe this in a three-dimensional integral. So what I'm going to do is I'm going to imagine that all the xy's that I have to worry about here are described by this sort of circle that sits in the middle of that object. So if you cut this in half and you laid it out open, the x and y values that we're working with all look like this. They all lay inside this circle, which looks like x squared plus y squared is less than or equal to 4. So that boundary circle is x squared plus y squared equals 4. Every xy on the inside will correspond to a point that's in here. And notice that that gives me a way to go up and touch the paraboloid sitting on top and come down and sit and hit the hemisphere on bottom. And so for any xy that I feed in, I have a well-defined change in height or change in z that I can integrate through. So when I look at this, I think, okay, if I was going to set this region up, the first thing I want to say is what do the z values range through? So given a point xy that's contained inside here, then if I have an xy value that are fixed, the z values that I range through start on the bottom with well, we have to solve this equation for z. So we're going to get z is equal to the square root of 4 minus x squared minus y squared. And because we're looking at the bottom hemisphere, I have to put a negative on it. And so that's the basic idea, is that that's our sort of lower z, and then our upper z was given to us as 4 minus x squared minus y squared. So if I wanted to calculate the volume of this region, I might start by saying, like, well, given an x and a y, my sort of top z is equal to the square root of 4 minus, my top z is 4 minus x squared minus y squared, because that's the z value that corresponds to this parabola at the top. And the bottom z value for that is minus the square root of 4 minus x squared minus y squared. So I can start to think about what this would be, the triple integral over w of the function 1 dv, if I want to think about it in xyz coordinates. The interior integral here, if I want to use Fubini's theorem here, I would write this as, well, I don't know what the outside integrals are going to do yet, but I know the innermost integral is going to be a dz integral. And that we'll figure out what dy and dx are going to do in a second. And that the z values are ranging from those exact things that we just wrote down, minus the square root of 4 minus x squared minus y squared, up to 4 minus x squared minus y squared. And suppose that we're just working with function 1 because we're trying to find the volume. Now the next thing is, okay, well that gets me this part. Now I know that I've integrated in the z correctly given the x and y. Now I need to figure out a way to describe the x's and y's in terms of one of the variables. So one dependent and one independent. Now we're just back to a regular old 2-variable problem. So I'm going to let one of the variables range independently and one of them move between two curves. The easiest way to do that is actually, I think anyway, is to think of the x values as running from -2 to 2, and think of the y values for a given value of x. The y values are ranging from y is equal to the square root of 4 minus x squared on top, down to y is equal to minus the square root of 4 minus x squared on the bottom. So given an x value, I know what the heights I have to go through, and then I can integrate through all the x's. So that would mean that I would integrate next dy, and I would integrate from the square root of 1 minus x squared negative, so not 1, 4 minus x squared negative to 4 minus x squared positive. And then finally, what x values do I use? Well, the x values correspond to all the possible x values that let me sweep out that circle, which are the values from -2 to 2. Now, I don't know if you can tell, but this integral is not necessarily an easy one to do because there's going to be square roots and stuff running all over the place. So this is an example of setting up one of these integrals. And the idea here is that when you're finished, this is the volume of that shape. This is the volume of that paraboloid with a hemisphere stuck to the bottom of it. Okay. So it's the general sort of way of approaching these triple integrals. So now let's do another example, but one where we can actually compute the integral. So I might give you a problem that says, suppose that we start with a tetrahedron that is defined in the following way. So here's it. All right, so here's the example that I want to talk about, the second example. So we're going to be working with a shape defined by a surface. So in this case, it's a tetrahedron. The tetrahedron is cut out by the plane defined by 3 points. We put a point, one on the z-axis and one on the y-axis and one on the x-axis, and we conjoin those with a point. And then we're going to assume that's the volume, the region that we're interested in integrating over. But this time, let's actually give it a density function. So let's imagine that the density of material in this region varies according to this function. F is equal to 1 plus xy. And we're going to try to find the total mass contained in the region. And so that means that we're going to be integrating over the region the density function dv. So the approach to this is going to be the same as it was last time in the earlier example, where we're going to have to find a way of describing z in terms of x and y, and then y in terms of x, and then we'll figure out x values that everything traces through. So at least for this kind of region, I mean, you could do it in any order you want. You know, you could x in terms of z and y, and then y in terms of z if you wanted to. Like that's what it means to be an elementary region. But for this one, let's do z in terms of x and y, and then y in terms of x. It seems a reasonable thing to do. So the first thing we're going to look at is I need the equation of the plane that defines the height of the function. And so it turns out to be the case that the equation of that plane is x plus y plus z equals 1. So the plane is given by x plus y plus z is equal to 1. And so if I think about a point located on that plane, sitting over some point xy in the xy plane, then its height is going to be given by z is equal to 1 minus x minus y. And that's sort of the top where we actually hit the surface. And the bottom is, we're thinking about the tetrahedron, so it's sitting on top of the xy plane. So it's going to be z equals 0 on bottom. And so before I even get to the x's and y's, I know that my interior integral is going to look something like the integral from the bottom height to the top height for a particular x and y value of the function we're integrating, which is 1 plus xy, and that's a dz integral because it's heights that we're measuring. And we still have to figure out what goes here and here, and either dx or dy on the outside, which means I have to think about how to take that xy region and cut it up into y in terms of x, and then some x variables. So if we think about the shape that this region is sitting over the top of, and I translate that into sort of a projection onto the xy plane, it looks like this. So there's x is equal to 1, there's y is equal to 1. The bottom of that tetrahedron looks like this. I've already figured out how, given a point x, y, to figure out the height of the tetrahedron above that point. So now I have to figure out how to chop this region up in terms of the y and x's that we did in the double integral section. So I'm going to note that this equation up here is y equals 1 minus x. And so this region would be completely described by y values range between 0 and 1 minus x, when x ranges between 0 and 1. And that's enough to finish writing down the integral. So our y, given an x, our y values range from 0 up to the curve, which is 1 minus x. So I can put 0 to 1 minus x, and this will be a dy integral. And then those x values can be located anywhere on this interval from 0 to 1. And at this point, this is just a routine integration. So let's just do it real quick. Integral from 0 to 1, integral from 0 to 1 minus x. I guess we love algebra. Integral from 0 to 1 minus x minus y of 1 plus x y dz dy dx. And notice the order of integration is actually indicated by the dz dy and dx. You work from the inside out. Okay. So this is the integral from 0 to 1, integral 0 to 1 minus x of z plus x, y, z, evaluated from 0 to 1 minus x minus y, which gets us the integral from 0 to 1, integral from 0 to 1 minus x of 1 minus x minus y plus xy times 1 minus x minus y dy dx. As we continue here, 1 minus x minus y plus xy minus x squared y minus xy squared dy dx. Notice no z's are left in the equation once we've completed the dz portion of the integral. Now we're going to eliminate all the y's. So when we're finished with this step, there should be no y's remaining. So integrate with respect to y, and we're going to get y minus xy minus 1/2 of a y squared plus 1/2 of an xy squared minus 1/2 of an x squared y squared minus 1/3 of an xy to the third. And so we will evaluate that from 0 to 1 minus x, which is sort of an unfortunate amount of algebra. So we'll call that dx integral. What this reduces to is a rather gnarly looking equation, I guess, by the time you're finished, because you get the integral from 0 to 1 of 1 minus x times 1 minus x minus 1/2 times 1 minus x squared plus 1/2 x 1 minus x squared minus 1/2 x squared 1 minus x squared minus 1/3 x 1 minus x to the third dx. And yeah, the algebra starts to get a little crazy in these things when you have lots of terms like this. If you actually go one step, but the key thing to note here is that there's no y's left. We've integrated out the z in the dz step. We've integrated all the y's out in the dy step. Now the only thing left is x's. If you finish this up, I think you end up with 7/40 as the final answer. It's probably not worth watching me work my way through the rest of it. The examples I'm going to assign you to do here are going to be simpler than that. Okay. So the upshot is that what I would like you to know about triple integrations is just that idea of taking a three-dimensional region and figuring out how to represent the z values as a band that goes between, for a given point x, y, how the z values vary, and then for a given x, how the y values vary, and then how the x's vary. Regardless of which variable you start with, that process is going to be the same, and the process of constructing a triple integral basically works the same. Thematically, you should keep in mind that when we think about triple integrals, we don't think about them as slices and slices and slices. From an intuitive standpoint, we're supposed to think of little tiny cubes that have values assigned to them. And what we're doing when we integrate is we're sort of averaging up or adding up all of those little values across the interior of some three-dimensional region. So it really does behoove you to think of it as density, and you're integrating density that might vary through a surface to figure out the total mass. All right, so let's talk a little bit about change of variables in the next video. This is the conclusion of the stuff I want you to know about 5.4. The next video will cover stuff on 5.5.